cumulative wind turbine installations have grown rapidly over the last 2 decades. Even by conservative estimates for future development, installed wind power generation, which currently exceeds 360 gigawatts, is expected to exceed 760 gigawatts by 2020, making this form of renewable energy an important component of modern energy systems. It has become apparent that as part of global efforts to address global warming, the transportation sector will have to undertake some drastic changes to be sustainable. This includes an accelerated phase-out of fossil fuel-dependent vehicles, alongside continued growth in renewable energy sources, to ensure electric vehicles run on the cleanest power. EVs have zero tailpipe emissions and are already low carbon compared to petrol and diesel vehicles, but their full potential will only be reached when the energy that fuels them is zero emission too. Combining the widespread use of wind and solar power generation with rechargeable electric vehicles appears to be a promising solution to reduce energy costs and emissions. Grid-connected PEVs with smart charging strategies can be an effective way to integrate off-grid renewable electricity generation, smooth the charging curve, contribute to system stability by providing regulation services, and move unhealthy emissions out of urban centers. For the last several decades, the advances of electronically switched semiconductors, in the form of power electronics, have made AC motor drives gain more prominence over the DC machines in industries, since they allow a direct connection to power grids via grid-connected power converters and have a more reliable physical structure. The grid-connected 3-phase power converter has wide applications in renewable energy generation. When electrical drives and grid-connected 3-phase power converters are combined together as one unit, it will provide a direct connection for the electrical drives to the power grid for electromechanical energy conversions and renewable wind energy applications. In the context of control system design, electrical drives and grid-connected 3-phase power converters share similar characteristics in their dynamic models and use the same type of semiconductors as actuators in the implementation of control systems. Since PID control systems are used in the majority of industrial electrical drives and power converters, understanding these control systems and having the capability to design and implement them are important to a control engineer. In this block diagram of a grid-connected 3-phase voltage source converter, the symbols denote 6 bipolar switching inputs, with either value of 0 or 1, for an upper and lower leg of each phase respectively. These switching inputs are conducted in a complementary manner. For example, at any given time, we have this combination. This means that only one of the switches is allowed to conduct at any one time. Before proceeding to the model derivation, several assumptions are made about the operation of the converter, like for the induction motor and PMSM in this playlist. Firstly, it is assumed that all switches are ideal and operate in a continuous conduction mode, and the grid voltage is symmetric and balanced. Secondly, the system is assumed to be a 3-wire system, thus, the sum of 3-phase currents and voltage is equal to 0. Thirdly, it is assumed that the inductance and resistance parameters are ideal, therefore, they have the same values for the 3-phase system. Even though these assumptions are ideal and do not hold entirely in applications, their acceptance ensures the derivation of the dynamic model in a simpler manner. Use of space vector simplifies the derivation of voltage equation for the 2-level voltage source power converter. The space vector, like for the AC machines in the last playlist, for 3-phase grid current, can be written as, while the space vector of 3-phase voltage at the 3 nodes on the grid side linked with the converter is defined as, and the space vector of the 3-phase grid voltage is described by this equation. Based on these definitions, the space vector voltage at the nodes of the converter satisfies this voltage equation. Next step in the derivation of the model is to convert the model in the space vector form to the model in the alpha-beta reference frame. By representing the space vectors, voltage and current, in terms of their real and imaginary components, they can be written in the complex notation. To obtain the dynamic model in the alpha-beta reference frame, The above variables are substituted into the space vector model, where the rotating frame in the alpha beta has the same velocity as the rotating speed of the space vector in the grid. Thus, by simply taking the components in the real and imaginary axes in the alpha beta reference frame, the electrical model of the voltage source converter is described by the following two differential equations. In the next video, we will model this power converter in the DQ reference frame so that we can use the model for the regulation of the output voltage.